Good evening, everybody, and welcome to The End of the Universe, which is the 6th lecture in my series on cosmic conclusions. How is it that we humans on this rocky planet can say anything at all about how the universe will end? After all, a cursory glance at the night sky might initially lead us to think that all is serene and static and unchanging. But careful study and painstaking investigation convince us that our galaxy and all the other galaxies out there, and there are many, are teeming with activity and energy exchange and matter relocation. As we peer deeper into space, we see that we live in an amazing universe. The fact that it is teeming with activity is a joy to study. But what makes us think it will all come to an end? How can we, as humans on this rocky planet, say anything definitive about the future of the universe, still less how it will be game over? Our place in space is pretty modest and humble after all. Our solar system is but a tiny speck in our galaxy, the Milky Way. Beyond our solar system, there are much more massive stars, there are white dwarfs, there are black holes, and, as I've said, there are many more galaxies. We do have a very limited vantage point, though. We're very far removed from having all the answers. But in the last century or so, we've come a long way, and we do have some quite good answers. But the nature of doing anything in research is all about being surrounded, not so much by answers, but by questions. That's the most exciting part of research, learning new things, making new discoveries that we chew away at and persist. And if you might be tempted to think that I'm making rather a meal out of that, let me tell you what the Nobel Prize-winning German physicist Albert Einstein had to say. If we knew what we were doing, it wouldn't be called research, would it? So what can we know, and how can we know it? Asking good questions gets us a long way. Do we know if the universe is static? Is this something that's knowable? Yes, it absolutely is knowable, and no, it is not static. Throughout this lecture, I'll be mentioning a few ways in which we know that to be the case. Just consider, to start with, that we live in a universe that is infinite, it's homogeneous, that means it's pretty much the same everywhere else. This galaxy, this group of galaxies over here is pretty much like this group of galaxies over here, and it's static, it's enduring forever. Just hypothesize that we live in that kind of universe for a moment. Now suppose that the stars are switched on forever, and then all of a sudden you have a prediction that the sky would be bright at night. But we know it's not, at least if we can get away from London to Cornwall or to Scotland or out into the desert. The night sky is dark, and that's a very simple but a very powerful piece of information. And it is consistent with the fact that the universe is finitely old. It has a fixed age, we think it's about 14 billion years. It is not infinitely old. Also, the speed of light is finite. Information doesn't travel infinitely quickly. And, therefore, only finitely many stars can be observed from where we are here on Earth. But already, that tells us that we are not dealing with an infinite, enduring, static universe where light travels infinitely rapidly. That's important in the paradigms we're going to explore today. Cosmology is different from other sciences. it is like the vast majority of other sciences, and probably here I'm excluding everything except pure mathematics. There is no such thing as scientific proof. All we have is evidence gleaned empirically, and that's absolutely true in cosmology. But we have to make some really big assumptions. We have to presume that the portion of the universe which is observable by us, the observable universe, is representative of the entire cosmos, including that which we cannot see. We also presume that the laws of physics, which have controlled the evolution of the universe to date and will govern its future evolution, are those that we have verified and tested here on Earth and within the solar system. That is one of the areas where we get a bit unstuck. But on the plus side, in cosmology, the past is accessible. It is observable. It is measurable. And that comes back to the fact that the speed of light is finite. It is not infinitely quick. Let's take a look at this beautiful image of the southern sky, which was captured by my friend and instrument scientist colleague on my Global JetWatch project, Stephen Lee. This is a very familiar image in the southern hemisphere, having, as it does, the Southern Cross. If we take a closer look at the star indicated by the red arrow over there, that is a star which is known as Proxima Centauri. Proxima Centauri is a distance of 4 light years. There is an important clue in the unit of distance we are using here, 4 light years from our solar system. As I've said, because light travels at a finite speed, not infinitely fast, that means that the propagation time for the information has important implications for when the information gets received. So if you consider an observer on a planet in orbit around the star that is nearest to the solar system, Proxima Centauri, it would only around now be able to be picking up my inaugural lecture as Gresham Professor of Astronomy. I talked about all the ramifications of the finite speed of light in that inaugural lecture, which was entitled Faster Than Light ? And the question mark matters, by the way. But it's perhaps worth noting it will be 2027 before an observer on a planet with very sophisticated equipment would be able to see this, my valedictory lecture as Gresham Professor. If we now look a little further afield to somewhere a bit more distant from the solar system, then we're looking further back in time. So this is the Fornax cluster of galaxies, and we're seeing it as it was about 1 million centuries ago. So now consider an observer on a planet orbiting one of these stars in Fornax A, this beautiful galaxy that's shown here. If that observer is equipped with really sophisticated, really sensitive technology, then they might even, looking back at Earth, be able to see the dinosaurs stomping around on Earth. They might even be able to see the asteroid that is purported to have wiped out the dinosaurs here on planet Earth. That information is propagating out in the universe. So if we understand this, then we can look at greater distances and further back in time to when the universe was much, much younger than it is now, and understand how it's developed from that time to now, and thence extrapolate to the future. But we've got lots of other tools in the toolkit to observe the cosmos. We have the entirety of the electromagnetic spectrum, all of light, from long wavelength, which is the radio, which was the subject of my first lecture in my series on cosmic vision. And the importance of studying the universe at different wavelengths from light, which our eyes are sensitive to, is that we see a different picture. Here is a projection in the so-called galactic coordinates, that's the longitude of our galaxy going across the centre there, showing where different parts of the optical sky fit together. If we zoom right in the centre and look at that same region of sky at radio wavelengths, we see an amazingly different picture, again teeming with activity. This image was produced by my friend and colleague in Oxford, Ian Hayward, and Isabella Ramallah, who's at Rhodes University in South Africa. And zooming in to all the beautiful features at the centre of our galaxy at radio wavelengths speaks of sparks flying and all sorts of explosions which are simply not apparent to us via normal visible light. But all this will fade away, as all the electrons, the relativistic electrons that are responsible for giving us the radiation at these longer wavelengths, as they radiate away their energy, they will dwindle, and then sooner or later we will see nothing where now we see a hive of activity. We can also learn about the contents of the universe, not just from the electromagnetic spectrum, but from particles that come and thwack here on Earth. This was the subject of my lecture entitled Fast and Furious, which I think raised amongst some people expectations that I might be talking about cricket. Well, I don't know very much about cricket, but there is a connection, because cosmic rays, particles, protons, the centres of atomic nuclei with the highest energies that come from outer space have, even though they might be individual protons or nucleons, have about the same kinetic energy as a cricket ball when thrown by someone more expert than me at cricket. The amount of energy that implies tells you that you must have the most amazingly efficacious sites of acceleration in the cosmos. Extreme acceleration, by the way, is beautiful physics. It's all about shock physics, and that too is a joy to understand. But this too will pass. As matter expands, where it's overpressured with respect to the rest of the fairly empty outer space, as energy is dissipated, as it is radiated away, these too will fade. On a slightly cheerier note, we can also learn about the cosmos when space-time itself vibrates and rattles and rolls. And this is particularly pertinent to the evolution of the universe. It was discovered in 2016 that space-time itself shakes in response to the coalescence of objects that are sufficiently compact and massive that they themselves distort space-time. When you have two black holes that come together, or a black hole and a neutron star, as they orbit around one another, gradually radiating their energy away and inspiraling, at that moment of coalescence, space-time will react. We will see space-time contract, and we will see space-time expand. And the expansion of space-time, which we have measured in such exquisite detail in coalescences of black holes, is highly relevant to cosmic expansion and evolution. In case you're a little bit uncertain what I might mean about stretching and compressing of space-time, let me demonstrate this to you with the assistance of my predecessor, the 9th Gresham Professor of Astronomy, Sir Christopher Wren. The effect is a little bit exaggerated, but this is what would happen if a big gravitational wave were to pass through London, stretching and compressing in the different dimensions. Let me emphasise this is measurable in exquisite detail with a wonderful facility in the US called LIGO, and this was the subject of my lecture on spacequakes. But if we're thinking about the end of the universe, what exactly do we mean? Are we talking about something that just blinks out of existence? Well, there are models that think that could happen, but they really are very gloomy indeed, and I'm not going to be touching on those tonight. But I do want us to think about what happens to the contents of the universe and what happens to space-time itself. This is an image of a rather beautiful galaxy that I took in just a few minutes of observing time under not great conditions at my observatory in Eastern Australia a few days ago. What's going to happen to that in the fullness of time? Is it just going to fade away? It's not as simple as that. The behaviour is much more rich than that. What ingredients in galaxies like that are going to fade away when? Well, first of all, I'm going to talk about things called planetary nebulae. These are not planets. These are what happens when a star, much like our sun, eventually evolves into a white dwarf. Planetary nebulae are the peonies of the universe. The peonies in my garden are absolutely glorious at present, but I have a feeling when I look at them tomorrow morning, faded dead on the grass. They don't last long at all. And objects like planetary nebulae, where you have shocked gas that you can see expanding with age, you can see light from it arising from all the different chemical elements that are present, they will gradually expand, and as they do so, as they radiate away their energy, as the densities decrease, these too will fade and dwindle. Right at the centre of these beautiful planetary nebulae starts out being a white dwarf, which is just a hot lump of stuff. But as the temperature cools there, in the fullness of time, after several billion years, it becomes a black dwarf. It becomes undetectable unless you actually accidentally walked into it in the night. This may be a bit gloomy, but let me press on. Let me tell you what is not going to be the end of stars and what is not going to be the end of planets. Now, collisions, as I've already indicated, happen between pairs of black holes, black hole, white dwarf, as I indicated in the previous lecture on spacequakes, but also collisions happen in outer space between galaxies when they're close enough for gravity to dominate over the stretching and the expansion of space-time. So if we take our nearest galaxy that resembles our own Milky Way galaxy, this is called Andromeda, it's moving towards us. It's got a bunch of other galaxies nearby, we call these satellite galaxies, that are all hurtling in towards the centre of Andromeda under gravitational attraction as it is attracted towards the Milky Way. Should we be afraid of this? Not this bit of my talk, no. Because although the galaxies, Andromeda and the Milky Way, will attract one another, the chances of any one star hitting any other star are remarkably tiny. And that's because, even though we might think that our sun is rather big, actually, relative to the space between different stars, it's absolutely tiny. All of the simulated, all of the behaviour in this simulation doesn't predict any star-star collisions. And yet we go from two beautiful galaxies to one slightly messed up, not quite so pretty looking galaxy. But we do see evidence of galaxies that resemble the one like this in the simulation. So this is the antennae galaxies discovered by William Herschel in 1785. This reassures us that the simulations we make are on the right tracks. So we're building up quite a good tool in the toolkit, and that toolkit equips us to make some sensible suggestions about how we think the evolution of the universe is going to play out. If space-time is stretching, and we'll come to that, these kind of galaxy-galaxy mergers will be a lot less frequent. Why does that matter? Maybe you think it's a bit safer that way. But actually, as galaxies collide with one another, as the tidal forces impact on one another, gas will get ripped around and compressed during the successive flybys And that compression of gas, that high density gas, will give rise to the formation of new stars. Conversely, if there are no galaxy-galaxy mergers, then we won't get ongoing star formation in the universe. But at least we've got some idea that at present, at this particular, probably rather special epoch in the history of the universe, and by epoch I probably mean 10 billion years, something like that, we probably have understood the laws of physics fairly well, not just in terms of gravity, but also in terms of a very important law of physics that we term the law of conservation of angular momentum, that property that bodies have because they're spinning. When you get a gas cloud that's spinning, then that will mean that as gravity starts to collapse it into a plane, it will still keep spinning and spinning and spinning. And sure enough, sooner or later, we'll get a star right at the very centre of this potential well, at the centre of this gas cloud, but we'll also get some planets forming. We'll also get protoplanetary disks that give rise to the moons, like those we know to orbit Jupiter and Saturn. So the fact that our simulations match with our observations gives us confidence that what we're going to predict for the future behaviour of the universe is probably not very wrong. So as we get closer towards the end of the universe, are planets themselves going to end? Well, I did discuss this a certain amount in my previous Gresham lecture. I talked about the fact that planets could run the risk of being quite battered by asteroids, such as this rocky one here, which thankfully kept a safe distance from Earth. I talked about one that did a very close flyby in my previous lecture on the end of life on Earth. But we only have to look at the Moon and look in close detail at its craters to see that things colliding into planets and their satellites are most definitely a thing. And I discussed the danger that these present to Earth in my previous lecture. So that could bring an end to that particular ingredient of life on Earth. That was in that particular lecture. But what about stars themselves? Well, the risk of big asteroids from far out in the solar system colliding with our planet isn't the only risk that planet Earth faces. As our own sun evolves, it's going to subsume planet Earth. And this was something that I discussed in a couple of lectures in the start of this series on cosmic concepts, where I made the point that exactly how stars themselves ends depends ever so much on the mass of the star. Stars like our sun will expand into and beyond their own planetary disks, subsuming them. Opinions differ as to whether when our sun expands into a red giant, it will stop at Venus or it will also engulf Earth as well. As we were discussing earlier, the smart money is on moving out to Neptune because it'll be a lot warmer out there by then. But massive stars evolve completely differently. They explode as supernovae, as I talked in another of my lectures. Stars like our sun, the so-called low-mass stars, will fuse all their hydrogen into helium, and then that will start fusing, that will collapse, that will heat up dramatically, that will increase the diameter of the star, and thence it subsumes the planets in its way. The end of massive stars was the lecture where I talked about the big stars that explode. So this too is all a bit gloomy, but let's turn to black holes. As attendees at my earlier lectures know, I love black holes. I work hard on black holes. They're a big feature of my research, my day job, and indeed my night job. They are the ultimate in collapsed matter. So surely, black holes will endure. Actually, let's just start thinking. A lot of the spectacles that I talked about in my lecture where I first introduced black holes, The End of Matter, talked about the spectacular phenomena that play out when matter gets too close to the event horizon of a black hole. And these are truly spectacular. This is one of my favourite black holes. These are some images I made in past years. This object, this black hole system, inspired my entire global jet watch round the world, round the clock endeavours. How can things this beautiful not endure? Well, look at the peonies in our gardens. Being beautiful isn't enough for them to endure. And I have some bad news. This object, this black hole, will only exhibit this spectacular behaviour as long as there is matter for it to guzzle and spit out and spin out. When that supply of fuel dries up, they will be undetectable. But is that the end of black holes? Actually, no. That's when a completely different process, hitherto undetected, starts to play out. There's a phenomenon which has been hypothesised by Stephen Hawking, pictured here, back in 1974, arising from the quantum vacuum fluctuations surrounding black holes, which works as follows. For a very brief period of time, it's possible for matter-antimatter pairs to blink into existence and blink out of existence once again. That doesn't violate the laws of physics as we understand them. But actually, quantum mechanics near massive objects, that's a particularly shaky foundation at present. But anyway, let's go back to the matter-antimatter particle that suddenly get winked into existence, thinking it's only a temporary arrangement. What do I mean by matter-antimatter pair? Well, I might mean an electron-anti-electron pair. An anti-electron is affectionately known as a positron, oppositely charged to the electron itself. But supposing one is a bit nearer the event horizon of the black hole and slips in, while the other stays out and can make a bid for freedom. If that happens, and by if I mean when, we're talking about cosmological timescales, then energy has got away from the vicinity of the black hole, and energy, by Einstein's famous relation, E equals mc squared, has diminished the mass of the black hole. So if you wait long enough, and I do mean long, we'll talk about how long I mean in just a second, then you will actually witness, if you're around, you won't be, if you could witness the evaporation of black holes. Let me be absolutely clear, it's undetected to date, but it couldn't possibly be detected to date because the radiation luminosities that are predicted are utterly minuscule in comparison with the radiation that comes from matter doing its stuff, orbiting very close to black holes, some of it getting swallowed, some of it getting spat out dramatically. So it in no way dents the evidence for Hawking's theory, the fact we haven't detected it yet. But how rapidly a black hole will escape depends very, very strongly on the mass of the black hole. But I cannot overstate how slow this process is. So let's take a look at a graph and understand how the radiation timescales, the evaporation timescales for black holes, depend on mass. So on the horizontal axis that I've got here, we've got mass expressed in units of the mass of our sun, which is an extremely convenient unit we use a lot in astrophysics and in cosmology. On the vertical axis, we've got time in Earth years. And the red line indicates the relationship between the time taken for a black hole of a given mass to evaporate into nothingness, to radiate away into a uniform soup across the universe. Let me help you calibrate some of the lines and numbers on this graph. So obviously where we have the number 1, that's the mass of our sun. Let's just go through a few masses first, and then we'll think about timescales. The next one is the mass of our Earth. This is the mass of the Barbican, where we're gathered today, and this is the mass of an elephant. If you could have a black hole that was so low in mass, it only weighed the same as an elephant, then it would evaporate away in the blink of an eye, less than the blink of an eye. If we could turn the entire Barbican into a black hole, obviously we really don't want to do that, that too would blink away rapidly. But what about more astronomically relevant timescales? So this horizontal line here is an Earth year. And as you can see, it's only black holes that have, relatively speaking, astronomically speaking, the most minuscule masses that would evaporate away on timescales that we as humans can relate to. A second is down here, but the age of the universe is only on this top blue line here. So if you had a black hole whose mass was the mass just of planet Earth, which is way less than 1,000th of the mass of the Sun, that wouldn't evaporate in the age of the universe to date so far. It would take way longer than 14 billion years to evaporate. The Sun, that would take something like 10 to the power of 60 years to evaporate. And that exponent there has 60 zeros. It's a huge number. So, yes, black holes will ultimately evaporate, but no one's going to be around to see them. Certainly not in this solar system, because the Sun will be long past its stage of enveloping all the planets it's going to envelop as a red giant. It will be long past its white dwarf stage. It will be very much into its black dwarf stage. There will be no life on Earth at that point. So we conjecture that this is how the black holes ingredient of the universe are going to play out. They're going to evaporate. There's going to be nothing to show for all the spectacles and all the brilliance and all the quasars and all the relativistic plasma jets that they entertain us with now. But let's now look on larger scales and think about space-time itself. Believe me when I say one of the easiest measurements to make in astronomy is measuring speeds. It's actually much, much easier than measuring distances in astronomy. Speed is extremely easy to measure in astronomy, and speed is amazingly important in making intelligent statements about how the universe is evolving. They give a really good clue as to what happens next. Speeds are the means by which we invoke matter, the existence of matter for which we have no other evidence. But I'm getting ahead of myself. I'll come to that in a minute. Detecting speeds is really easy if you have a wonderful piece of equipment attached to your telescope called a spectrograph. And here is a photograph of just the central bit of the spectrograph that I have installed at my school observatory in South Africa. It was designed by my friend and colleague in Australia, optics expert Steve Lee, and it's just brilliant for measuring speeds. When we see radiation that we know exactly where it's coming from, if it's coming from hydrogen light, but we measure it to have shorter wavelengths than normal, we know it's coming towards us, and with what speed. If we see light that we also know for sure is coming from hydrogen to be at longer wavelengths, we know for sure it is moving away from us and how fast it is moving away from us. This is something called the Doppler effect, which is familiar in all sorts of contexts. If in the rest frame of some kind of emitter, be it a light emitter or a sound emitter, in its rest frame, if you have symmetric radiation, then this is what you'll see. But if you're moving towards something then what's moving, when the source of the waves is moving towards the observer, you'll see shorter wavelengths. When it's moving away from the observer, imagine an observer on the left-hand side of the screen there, you'll have longer wavelengths. We can totally convert that via very simple equations, even if we're talking about relativistic speeds, into the actual speeds. So we can measure speeds all across the universe. But this is when we start getting presumptuous again. What do we take as markers across the cosmos? We take entire galaxies. We measure their speeds, and most galaxies, by the way, are not like Andromeda, which is hurtling towards us and going to collide with the Milky Way, as I said, in several billion years' time. Most galaxies in the universe, the vast majority of galaxies, basically everything outside our local group of galaxies, is separating from us and separating from us and going away from us at faster speeds the more distant the galaxy is from us. Because everything is flying apart, we can extrapolate back in time, and we know that at earlier times everything was closer together. And this, with a few other pieces of evidence that I won't go into in great detail in this lecture, takes us to what we refer to sometimes as the start of time, the hot Big Bang. All of this makes use of the Doppler effect, which is such a convenient, such a straightforward tool in the toolkit, but with Slipher, with Edwin Hubble, with Georges Lemaitre. It was observed using that technique that the cosmos is absolutely expanding from us. All galaxies, apart from if they're really close together and gravity is dominating, all galaxies are moving apart one from another. The universe itself is expanding. So what are the consequences of this? What are the implications of this? Well, first of all, as I alluded to earlier, you won't get any more galaxy-galaxy collisions unless they've happened, relatively early on and, gravity has done its stuff and dominated. After a while, when space-time has stretched out, in just the same manner it does when a gravitational wave goes past because two black holes have collided, when the galaxies get too far apart, there's no possibility of them ever colliding ever again. They won't even be able to see one another because as space-time stretches out so far, and because light travels still at the same finite speed, there will come a point in the history of the universe when it won't be possible for any observer on any planet orbiting any star in any galaxy to look out and see any other galaxies. We are at a particularly special epoch in the history of the universe, a particularly special 10 billion years, because space-time hasn't expanded so much that we can't see those other galaxies receding from us. The fact that we can see the universe expanding now is really helpful in refining the models of cosmological evolution that we're able to develop. But the fact that galaxies are moving away from us, it's because space-time itself, the gaps between the galaxies, are expanding. The galaxies themselves are not expanding. Solar systems are not expanding. We are not expanding, unless we're eating too much pudding. Space-time is what's expanding. So because everything is flying apart, as I've indicated, the time will come when the universe is too stretched out for one galaxy to observe another galaxy. People will still be able to do astronomy, but all they'll see is just stars in their own galaxy, because gravity and angular momentum will still keep those going and keep the show on the road very, very locally. It will not be possible to figure out at that time that the universe is expanding. And as I've indicated, no more galaxy-galaxy collisions, no more star formation. This all fits in with the paradigm that I mentioned very briefly of the hot Big Bang, which, rolling back in time, the universe was much, much more compact. it was much, much hotter. And using the same projection of what's visible in the night sky to represent cosmic microwave background radiation, or at least if we subtract out our own galaxy in the middle there, it's the temperatures from this and it's the anisotropies, the ripples within this, that help us have very, very clear ideas about the nature of the hot Big Bang and the formation of atoms, which are pretty crucial for you and I to live and breathe and have our existence. But what is the connection between how much stuff there is in the universe and where it's all going to end up? What is the connection between the density of matter in the universe and the destiny of the universe? It may seem surprising to you that how much stuff we've got in the universe plays a huge difference to its ultimate fate. The picture that I've been gradually building up throughout today's lecture was far from being the reigning paradigm throughout the last century or even the last few decades. But knowing what's out there has been crucial at all times for refining our understanding of what's going on. I've constantly been coming back to, we understand the laws of physics, don't we? Conservation of angular momentum, electrodynamics, relativity, gravity. We understand gravity, don't we? Don't we? Well, here's the thing. We think we understand pretty well how gravity works on planet Earth. We can describe how satellites orbit around us. We can describe pretty well what's going on in the solar system. But when you extrapolate and make measurements and try and interpret on scales larger than our solar system, but on the size scale of an entire galaxy, so that's changing gears by about 7 orders of magnitude, it doesn't work. Gravity appears to be not giving us quite what we expect when we go up to these larger scales. We invoke something called dark matter on the basis of measuring speeds of gas within galaxies. And I hope I've emphasised to you that measuring speeds is really easy. You've got the right equipment, you can measure the speeds, you can start coming up with your astrophysical interpretation. The presence of dark matter is invoked by the way that gas evolves and rotates within galaxies. It's as simple as the diagram I'm about to sketch for you. So on the horizontal axis here, we've got the distance of a particular parcel of gas that's radiating light, say from hydrogen, from the very centre of the galaxy that gas is in orbit around. The blue dashed line is what we expect to see on the basis of Kepler's laws, which are a development of Newton's laws. So this is what we expect. We get further away from the galaxy itself, all the stars, all the black holes, all the good fun stuff, and we expect that as we get further away, any gas present being further away, but having the same amount of mass that we infer to be present on the basis of the stars that we can see, we expect that speed to tail off with increasing distance from the very centre of the galaxy. But that solid red line is what we actually measure. It's completely different. It's verified by observers all over planet Earth using all sorts of different equipment. No one disputes this sort of measurement and observation. So what's invoked is matter that we cannot see, matter that is not radiant at all, matter that is not, in the jargon, baryonic. Baryons are things like protons and neutrons that have fairly hefty amount of mass when you've got enough of it together. Dark matter is implied because when gas rotates around galaxies, it seems as though there's a whole lot more mass there than we have any evidence for if we're just thinking about the brightness distribution of stars arising from the stars in that galaxy. It behaves as though there is a lot more mass there, and that's why we call it dark matter. But we don't know what it is. We really don't. Billions of dollars have been spent on it, and we don't know what it is. And yet, these results of faster and faster rotation of gas in galaxies, that persists. No one disputes that, but still we don't know what that is. Now, dark matter accounts for something like 27% of the matter, the density that we know of in the universe. If you think that's strange, let me tell you about something called dark energy. So I've indicated to you that as you look at galaxies that are further and further and further away, they're receding from us faster and faster. And until a couple of decades ago, this seemed to follow the Hubble-Lemaitre law that the recession speed from our galaxy would be pretty much proportional to the distance from our galaxy. But then people started measuring things much more closely and much more carefully with a particular kind of object, a particular kind of exploding star known as a type 1a supernova. I'm going to show you a slightly complicated plot, but stay with me. On the bottom axis, you've got something here which is denoted Z. Z stands for redshift. I know redshift begins with R, but stay with me. Z for redshift. That maps to the distance of the stellar explosion that we're talking about. But what's on the horizontal axis here is a measure of the brightness on a very funky astronomical logarithmic scale. But it's the brightness. And if you plot what you expect for these particular specific supernova explosions called type 1a supernova explosions, they don't precisely follow the Hubble-Lemaitre law when you look closely. So this is a sort of a difference form of the upper plot shown here, and you'll see there's a preponderance of the points further out that tend to want to belong to the more solid line rather than the dashed line. So what's going on? Well, that solid line is a line that corresponds to a universe with something we refer to as a cosmological constant, a component of dark energy that functions as something that acts oppositely to gravity and accelerates the recession speed of galaxies away from Earth. Where you measure lower redshifts than you expect, given the standardizable candle nature of these particular stellar explosions, that it implies that you have slower expansion of space-time in the past than you do now, that the expansion is accelerating and it's acting to offset gravity. And the converse is true if you measure higher redshifts. But again, this result has been replicated by other groups around the world. The way galaxies move away from us seems to be accelerating with time. This is attributed to a dark energy component corresponding to about 70% of the contents of the universe. But we don't know what it is. But this discovery, which of course has strong implications for the evolution of the universe, led to the Nobel Prize being awarded to Saul Perlmutter, Brian Schmidt and Adam Rees in 2011. It was a really important discovery to make, even if, frankly, we still don't understand quite where it's coming from. It's not just a constant in the maths, it's manifested in physical reality. We can measure it with the speedometers that are our spectrographs attached to our telescopes. The discovery of dark energy considerably undermines our confidence in our expectations of saying how the universe will end. Winding back the clock before this discovery, people used to talk a lot about something called the critical density. The idea that the momentum due to the Big Bang and the expansion that followed from that would match exactly the pull of gravity from all the mass due to all the galaxies within, at least if you drew in dark matter. Well, not so simple. The idea was that, or the paradigm was, that if you thought about time, the age of the universe on the horizontal axis, the size of a box containing 1,000 galaxies would just get bigger and bigger, but the rate at which it would get bigger would slow down and slow down. That doesn't appear to be necessarily the case unless we invoke dark energy to make that work. Because the matter that we can see via light, the matter that we can infer by its effect on the gas rotation speeds in galaxies is insufficient to give this kind of behaviour. No one believes that there's too much matter density in the universe to give rise to the ultimate compression of space-time with time, reversing the hot Big Bang, returning to the size of the universe at the hot Big Bang, known affectionately as the Big Crunch. But if you have too much acceleration, if you've got less pull of gravity than you think is going on in the universe, well, it'll just keep expanding and expanding and expanding. No more galaxy-galaxy collisions, no more, ultimately, in a couple of tens of billions of years' time, no more being able to see other galaxies, because space-time will have stretched out too much. But all those other galaxies will be fading anyway. Obviously, all the massive stars will have done their explosions as supernovae. They'll have given rise to black holes. Ultimately, they're going to evaporate. The lower mass stars, well, brightness from them will endure for longer, but you'll get the whole red giant, white dwarf, black dwarf sequence that I laid out in my lecture on the end of our sun. So, how do we think it's going to end? The Big Crunch, as I've indicated, is now thought to be unlikely. This is a good thing, because although I hope I impressed on you that a galaxy-galaxy collision with the Andromeda Galaxy wouldn't be something we should be afraid of, the Big Crunch would be implying that space-time itself were contracting and contracting and contracting. None of this nice fly past and generating a new pretty swirly spiral pattern. So we now think that is unlikely. The so-called Big Rip, where matter just gets faster and faster. This is a variant of the so-called Big Freeze, where the rate of expansion of space-time just extends asymptotically. We now think that the universe is just flinging itself apart. This seems to be the most likely on the basis of the discovery of dark energy. But did I mention we don't know what dark energy is? Yeah. And so where are we now? We are here, and this is pretty close to the end. And how's the universe going to end? Well, it's going to end gradually. We think in all the most favoured models, it's going to be increasingly cold as it gets increasingly old. There is no model in the research literature, there is no model propounded by anyone active in the field that has the material universe persisting, unchanging forever. That's not a thing. So, the end of the universe, when is it? It is billions of years away. Now, at the risk of stating the obvious, several billion years is quite a long time away. I don't want anyone to lose sleep over that tonight. What will I be doing in the meantime? I mean, you know, I'm reconciled to the fact my own life will come to an end, whether the universe ends sooner or my life ends sooner. I think I know which one will come first. But what will I be doing in the meantime? I will be renewing my efforts to decipher the dynamic, excitable, active universe. I will be doing my best to live life in all its fullness, I will continue to help others to learn and to learn from them and from the amazing universe in which we live. If you'd like to follow what I'm doing, this is the website of my global programme, and you're most welcome to follow that in the coming months to see what's going on. But right now, this is the end. Thank you.
Thank you very much, Catherine. I'm Martin Elliott. I'm the Provost of Gresham College, and I'm just going to ask the audience out there in the big wide world for some questions, and then we'll move quickly to those of you on the floor before we wind up. So I've got one here from outside. I don't know where, somewhere in the universe probably. A question about the time taken for black holes to evaporate. How do the time periods compare with the theorized time for proton decay?
Proton decay is a whole lot longer still. So you'll notice I carefully avoided defining what I meant by the end of the universe. Did I mean the end of galaxies? Did I mean the end of stars? Did I mean the end of compact objects like black holes? I didn't specify, but proton decay would be a whole lot longer, probably, depending on models.
So, I mean, can I just ask a question about the end? Because it seems to be, as you describe it, a progressive dilution of what's in there, and that the space between whatever we've got is getting bigger and bigger. It's not the end, it's just further apart.
That's absolutely true. I mean, apart from a couple of models that aren't anything more than, as it were, mathematical speculation, there's no sense in which anyone is seriously modelling that the universe will wink out of existence and truly have a very finite, abrupt, discrete end. I don't know if that's a comfort.
Of course, completely comforting. Can we have the house lights up a bit so I can see who's going to ask us some questions?
So what you're really saying is the universe is going to continue to expand. It is not going to suddenly change track and collapse in on itself. Is that correct?
It is correct that that is the reigning paradigm. But in the light of new information, we humbly change our minds.
Thank you.
There isn't an endless cycle of Big Bang followed by Big Crunch and the whole thing endlessly repeats. If that is not the case, isn't there a sort of philosophical issue here, because it implies that the Big Bang is a unique event and we need somehow to explain why it happened once and only once?
Well, the philosophical reality is that we think there really was a hot Big Bang. Yeah. The fact that it's singular doesn't strike me a priori as being any more philosophically reasonable or unreasonable than a static, unchanging universe. But it appears to be the way physical reality is. So we have to take it seriously and adjust our mindsets accordingly.
We have to move you to the Professor of Divinity, I think, for the answer to that question. And just at the front here, thank you.
I'm referring actually to your black hole. What I understand now is that some of the ideas have changed, and that when you get inside the black hole, there is a sort of vacuum, and there is some dark energy there, which has something to do with the dark energy that you were talking about, of expanding out. Could you just say a few words about that?
What I will say very politely, if I can, is that a lot of the models that purport to say this is what the inside of a black hole is like are really quite speculative, and I wouldn't hang anything on those models. Sorry.
Thank you for the presentation. My question is just towards the end of your presentation, really, when you said as the universe is aging, it's going to be cooler. How would you explain that in the context of the Earth? I know it's just one of the planets in the universe, but in terms of the Earth getting warmer, talking about that. Yeah.
So I was speaking about the universe as a whole, and you've picked on quite an important point, which I didn't go into, which is really that there's going to be, in saying the universe is cold, it's going to be a very dilute, homogeneous, evened out sort of place with no thermal gradients, no ability to do any work, no ability to drive some of the interesting phenomena that it's such fun to study. In the context of the Earth, we are, things are turning around inside us. Relative to the sun, we're not radiant at all, but actually we're giving off heat. If you observed this planet at an appropriately long wavelength, you would see thermal radiation from it. So gradually, this rock on which we stand will cool. We're talking about many, many billions of years, but it too will cool. And ultimately, the universe will become much more dilute and very equilibrated, and frankly, very dull.
So, Katherine, this may seem obvious to you, but I'm assuming that the entire model that you're describing means that the basic quantum of energy that exists within our universe does not and cannot increase from that original moment. Nothing's being added to it during this process.
As far as we know, nothing exciting is going to happen when we've reached this very dispersed, very cool, very dilute stage.
Thank you very much for the presentation. It was very, very interesting. And I guess I have somewhat of a question of an uneducated person who's just very curious about this thing. Among uneducated people such as myself, who are trying to find what's going on there, there is, I guess, quite an appealing theory that you can find in the literature or just in wherever you're getting your information from, that basically the Big Bang started from a black hole just because the singularity in its qualities is quite similar to what we think might have been the first point in the universe, which then created, from which the Big Bang happened. But then, given that in your lecture you said that the black holes are actually evaporating, and obviously it takes lots of time for them to evaporate, but then does it completely refute the version that the universe started from a black hole just by the virtue of the fact that the black holes are evaporating, and then the first point in universe can't be a black hole just because black holes evaporate and the first point in universe started expanding?
So I would urge caution in saying, because a black hole is a singularity, and because the Big Bang is a singularity, the Big Bang started from a black hole. I would really urge caution there.
Can we take, I'm afraid we've just got time for one more question, so
I was wondering whether there is any reason, scientific reason, for us to qualify what we call the known universe as the universe that we are capable of knowing within the limitations of our technological and mental ability. And I was saying that by mental ability, I just mean that I wonder whether we're hardwired to grasp models that fit with what we know of life. Things begin and end, and we might not be able to overcome this. Does it make sense?
I think I understand what you're asking. So perhaps the first point to make is that the knowable universe, if you're mapping that to the observable universe, no one is assuming that's all there is, because that would be a very constraining assumption to make. And it would be saying that we're very, very special at a very special point in the universe. So I don't think anyone would say that. Are we limited in our understanding of the cosmos by our human imagination and by our mathematical skills? Sure. We absolutely are. But with time, with persistence, with tenacity, with talent, with wonderful astronomical equipment, I'm sure we'll make more progress.
Thank you. Well, today is self-evidently a very sad day for Gresham College and for all of us who've been watching and listening to Catherine's lectures. We are extremely sorry that Catherine's term as Gresham Professor of Astronomy has come to an end, fittingly coinciding with the end of the universe. We're also proud, very proud, that Katherine chose to join the long and spectacular list of Gresham Professors of Astronomy, and she's more than held her own in that triumphant band. Her lectures have been brilliant. They've been fluent, authoritative, if at times challenging for the simple mind like mine. And they've been delivered also with great clarity, aided by her wonderful voice and pacing of lectures. She's going to return to her chair in astrophysics at Oxford, and as you've heard, travel more as part of the Global Jet project, Global Jet Watch project, firing up the imagination of young people all over the world. We're going to miss you very much, Katherine, and I hope you'll stay in touch and that we can invite you back and maybe to join your successor and colleague, Professor Chris Lintott, who will start as Gresham Professor of Astronomy in the autumn. But in the meantime, ladies and gentlemen, please would you thank Katherine Blundell in the usual way.